Welcome. Today we will talk about the mortality as a measure of disease impact. Death or mortality is unavoidable and it has a tremendous significance for each person. Questions such as when and how death will occur and will I be able to delay the inevitable are some of the most difficult questions to answer. In this chapter, we will try to quantify mortality to identify risk based on different types of disease. So our learning objectives are why mortality rates are useful, the difference between the four measures of mortality, all-cause mortality, case fatality, proportionate mortality, years of potential life lost, how to calculate them. I will tell you which ones you will be tested on and which ones you will not, okay? And finally, you need to understand the meaning and function of years of potential life lost, what are the 5-year survival rate is all about, and some common pitfalls of the 5-year survival rate. So let's get started. You probably wonder, why study mortality rates if we know morbidity deaths? Well, let's think about it. Morbidity rates or disease rates tells us the risk of the disease, meaning how many are affected, but we know nothing about the severity of the disease. By calculating mortality rates, we can identify diseases that pose the greatest risk for death, and then we can focus our treatment to delay the course. Also, we talked about how difficult it is to identify new cases of disease for diseases that have a long onset, such as cancer or cardiovascular disease. I want you to read these two statements and tell me which measure can we use to address the risk of dying from cancer. Is it the first one or the second one? The first statement tells you just the number of people who died from cancer and nothing more. The second statement provides you with denominator information, which tells you what was the total population when those cancer deaths occurred. Clearly, that gives us a more complete picture about the risk since the total population matters. This graph, found in your text as well, shows the number of cancer deaths per decade. From this graph, it is easy to conclude that cancer deaths went up over the years, but in reality, that would not be true since the graph does not tell you anything about the total population. How many people were living in the 1900s and how many in the year 2000? We know that the population grew as well. Thus, if we want to address the risk of dying, we need to deal with rates. In this graph, we can see mortality rates for several types of cancer in men from the 1930s to 2007. The most dramatic increase is death from lung cancer. You can see this blue line right here. Notice that this graph depicts the population on the y-axis, so you have right here rate per 100,000 people, and the year of death on the x-axis. We can see that lung cancer, for example, started to slow down since the mid-1990s, which may be the result of all the tobacco interventions that took place. So you can see here it has a steep incline, but kind of like slows down following the mid-1990s. Here's another important contribution of mortality rates. We can compare rates among sexes, among ages, and so on and so forth. From the graphs, you can see that lung cancer is a leading cause of death for both men and women, but it definitely affects more men than women. Here we can see that cancer is the leading cause of death among people under the age of 85, and cardiovascular disease is the leading cause of death for people over the age of 85. There are different types of mortality rates that we can calculate, and each one serves a different purpose. In this class, I only want you to be able to calculate all-cause mortality. In your next EPI class, you will learn about all of them. The calculation is pretty simple. For all-case mortality, we need to know the total number of deaths from all causes in 1 year, and we will divide this by the number of persons in the population at mid-year. Since it is a rate, time is important. Finally, do not forget to multiply with your base in order for your final answer to make sense. Sex-specific mortality rates are rates that show the number of deaths affecting a specific sex, men or women. Again, when you calculate sex-specific mortality rates, you need to be careful with what goes in the numerator and what goes in the denominator. If you're calculating women-specific mortality rates, it makes sense to only place the number of women in the population at mid-year in the denominator and not both men and women. Case fatality is a measure of disease severity. Case fatality is a percent and not a rate. It is impossible to know the exact time of disease development for certain diseases, which means it may be difficult to determine precisely when the disease process began. To calculate case fatality, we divide the number of individuals dying during a specified period of time with the number of individuals with a specified disease and not with the entire population who are at risk, like we did with mortality rates. And again, notice that this is a percent, so we multiply with 100 and not with a base. So what is the main difference between mortality rates and case fatality? Well, the denominator. Think about it. If you know the number of people who died from a disease and you know how many people have the disease in that population of interest at a specific time, we can see how large the percent is and we can decide whether it is really deadly or not. If you place in your denominator the entire population at risk, your rate will show you just the number of people dying per certain amount of people. It tells you nothing about the severity of a particular disease. So how do we use case fatality? We already talked about disease severity, but by looking at the percent affected, we can also see if new therapies or technologies reduce overall mortality rates. A decrease in case fatality would mean that we are getting better at treating a particular disease. Proportional mortality is another very important measure of disease occurrence. Proportional mortality is not a rate, and it shows us what proportion of total mortality in the US, for example, is due to a specific cause. For example, we want to see what proportion of deaths in the US are attributed to auto accidents. Thus, we will divide the number of deaths caused by auto accidents with the total number of deaths. Since it is not a rate but a proportion, we will multiply with 100 and get the appropriate percent. Again, so here you can see the proportional mortality in 2009 for the different age groups, okay? And you can see that proportional mortality for auto accidents is greater for younger people than it is for people over, for example, the age of 65, which are affected with very different problems than younger people. Proportional mortality plots may show a certain trend over time. Meanwhile, we also need to consider that the observed trend is affected by the mortality rates of other diseases, since we are dealing with proportional mortality. For example, in this graph we observed an increase in cardiovascular disease, which does not necessarily mean that cardiovascular disease went up, but probably the mortality rates of other diseases went down. Again, here you can view the relationship of mortality rates with proportional mortality. In the early period, we had 40 cases of cardiovascular disease per 1,000 people, and the proportional mortality was 50%. While in later years, the cases of cardiovascular disease doubled and the proportional mortality increased by 16.7%. The idea is that those two measures tells us two different stories, thus depending what we need, we have to select the appropriate measure. So let's solve a mortality word problem. So here we have Townsville, mid-year population 100,000. If we had to separate it by gender, it would be 50,000 males and 50,000 females. We know that 450 people in total die from all causes in 2011. 20 are sick from measles in 2011. Of those 20, 18 die from measles in 2011. And then 190 women in total die from all causes in 2011. We will use a base of 1,000. So let's see our calculation. So for all-cause mortality, rate in 2011, right? We will actually take the number of deaths from all causes at mid-year and we will divide it with the number of persons in the population at mid-year. So that means there were 450 people that died and the total population for this particular location was 100,000. Our base is 1,000. That means 4.5 per 1,000 persons per year. For case fatality, we will take the number of people dying from a specific disease at a specific period, and we will divide it with the number of people with a disease, and we will multiply it with 100 since it is a percent. So the case fatality for measles was 18 out of 20, since 20 people had measles, 18 died, right? So that means it's 90% of cases with measles will die. Proportional mortality would be equal to number of deaths from a specific cause in 1 year divided by the total number of deaths in 1 year multiplied by the 100. So we had 18 specific measles deaths. 450 is the number of total deaths, so 18 divided by 450, and we will multiply by 100. That means 4% of all deaths can be attributed to measles. And finally, for sex-specific mortality, we're going to take the total number of deaths in a specific sex at mid-year. In this problem, I gave you the number of deaths for females, which is 190. Now the population, the female population, is 50,000. Remember, there was 100,000 was the total population, out of which half of it was female. So 190 divided by 50,000, and we will multiply with our base, and that means it's 3.8 per 1,000 women. Years of potential life lost is another index used to help us set priorities. Years of potential life lost is a measure of premature mortality. Apparently, not every person will die at the exact same age, but for the most part, we have set a life expectancy for every single cohort. In the US, the current life expectancy is set to 75 years of age. That means for a baby who is born today, we expect it to live at least 75 years. Now, if that baby reaches maturity and ends up dying at the age of 73, for example, that means that it lost 2 years of the predetermined standard age. In other words, the earlier the age at which death occurs, the more years of potential life are lost. Years of potential life loss serves 3 important public health functions. It allows us to establish research priorities, surveillance of temporal trends in premature mortality, and evaluate effectiveness of program interventions. This figure shows the years of potential life lost in the US before the age of 75 years in 2008. The top bar shows the total potential years life lost from all causes, which always will add up to 100%. The bars below will show the individual potential years life lost from each leading cause of death, and the percent of each years of potential life lost from all causes for which it accounts. This figure shows years of potential life lost before age 65 for children and adults younger than 20 years of age. We see that the YPLL from injuries exceeds the effect of YPLL from congenital malformations and prematurity combined. Thus, if we want to have an impact in children and young adults, we need to look at the causes and address them. It seems that more than half are from injuries in this case, as you can see here. So now we're going to move on to measures of disease prognosis. So what is prognosis and how it differs from diagnosis? Based on the definitions given above, we can see that we need a diagnosis first in order to be able to prognose how the disease will evolve. Once we know what a person has through a diagnosis, then we can prognose them with what is coming their way. I just want to give you a heads up about the next few slides. Since we will not cover Chapter 6 in detail, I'm incorporating important information that relates to our topic in this lecture. Feel free to read the chapter, but know that I will not test you on the calculations covered on the chapter. So, how do we express prognosis? We have 5 different ways out of which you already learned about the first one. The 5-year survival is a very important term, and you need to know it well. The term is frequently used in clinical medicine, particularly in evaluating treatment for cancer. The 5-year survival is the percentage of patients who are alive 5 years after treatment initiated or 5 years after the diagnosis. It is a proportion and not a rate, and although it is used widely, we should say that there is nothing magical about it. Another approach is to use the actual observed survival over time, the median survival time, or the relative survival rate. Those three involve calculations that we will not cover in the introductory epidemiology. Going back to the 5-year survival rate, you may wonder, why use 5 years and not 2 or 7? How did we come up with that number? Well, the majority of deaths from cancer will occur the first 5 years after diagnosis, so it is an index of success, if you may. A major limitation of the 5-year survival rate is that it is affected by new technologies, which allow doctors to diagnose diseases very early. Thus, the 5-year survival will be affected by how early or how late a person is diagnosed and starts treatment. What are some issues with the 5-year survival rate? Well, as we previously stated, if a person uses a state-of-the-art facility and receives an early diagnosis, then it may seem that he or she lives longer, but the diagnosis happened so early that it took time to evolve. That is called lead time bias. Since we measure success rates based on a 5-year survival, that means we leave out everyone who does not make it to 5 years. Also, the 5-year survival tells us nothing about the quality of care or what the experience was for those 5 years. Again, here is a visual of lead time bias. If the disease was diagnosed in 2005 versus 2008, it may seem that the person survived longer, as you can see, but in reality it didn't. It was just the earlier diagnosis that actually contributed to the difference in survival. And that is the end of our lecture. Next week we will go to part B, okay? So have a good one. Let me know if you have any questions.